High in the Andes, amidst winding roads, gleaming white structures dot the mountaintops. These are modern ground-based telescopes, placed here due to unique conditions that make this location one of the best on the planet for studying the universe's mysteries. By the end of this decade, one of these, white, objects will become significantly larger than the rest. A colossal structure, nearly as tall as a 22-story building, will open its immense doors each night to allow the world's 7 largest mirrors to begin their work. This is the Giant Magellan Telescope, GMT, whose construction began back in 2015. It will produce images of the universe 10 times sharper than the renowned Hubble Space Telescope, and even 4 times sharper than the cutting-edge James Webb Space Telescope. Its unique design involves combining 7 state-of-the-art telescopes into one giant instrument, poised to become one of the 3 most powerful telescopes ever built by humanity. With the long-awaited James Webb Space Telescope now operational, we can confidently declare a new era in space exploration. It will be joined by advanced observatories such as the Nancy Grace Roman Space Telescope, with its incredibly wide field of view, and the European Space Agency's Euclid mission. Their primary goals include studying galaxies, galaxy clusters, and the evolution of the universe, as well as making new attempts to unravel the mysteries of dark matter and dark energy. However, this does not mean that ground-based observations are becoming a thing of the past. On the contrary, several key astronomical observatories are currently being built on Earth, promising to elevate optical and infrared observations to an entirely new level. Astronomers always strive to observe the faintest objects with maximum detail. But about 20 years ago, it became clear that even 10-meter mirrors were no longer sufficient for further scientific progress. More ambitious solutions were needed, giant telescopes capable of collecting many times more light than existing ones. The principle is simple: doubling the diameter of the primary mirror quadruples its surface area, allowing it to collect 4 times more light. An observation that previously took 4 hours can now be completed in just 1. Furthermore, detail is enhanced due to higher angular resolution. For example, 2 closely spaced stars might appear as a single bright object when viewed through a small telescope. But the larger the mirror's diameter, the better the telescope can resolve these objects, allowing you to see 2 stars instead of 1. Observation time plays a crucial role, especially when acquiring spectroscopic data needed to determine the chemical composition of exoplanet atmospheres. This requires observing a planet approximately 100 times longer than for obtaining a direct image. Large mirrors significantly optimize this process, reducing the time spent. However, the larger the mirror, the greater its mass, which creates significant engineering challenges. Moreover, large mirrors are susceptible to deformation under their own weight and even wind. Therefore, the maximum diameter of a monolithic mirror that can be manufactured is around 8 meters. But 3 giant telescopes of the future, set to begin operations in the next decade, address this problem. The extremely large telescope, ELT, currently under construction in Chile, and the 30-meter telescope, TMT, planned for Hawaii, will utilize numerous smaller mirrors working together as a single unit. Similar to the James Webb, each segment will be mounted on a structure with actuators that align the segments to form a unified mirror. This design is expected to achieve primary mirror diameters ranging from 30 to 40 meters. The Giant Magellan Telescope, being built at the Las Campanas Observatory in Chile, has taken a different approach. Instead of one large 25-meter mirror, it combines 7 8.4-meter mirrors within a single observatory. The resulting structure will resemble a flower, with one central mirror surrounded by 6 petals. Upon first glance at an image of this telescope, one might wonder, how will this even work? After all, large gaps remain between the circular segments, preventing the creation of a continuous surface like the James Webb. Furthermore, the segments are not positioned tightly together, with an average distance of about 30 centimeters between them. How will this affect deep space observations? Contrary to popular belief, astronomical photographs are not direct reflections obtained from the telescope's primary mirror, much like one from a bathroom mirror. Telescope mirrors serve to collect and focus light. Each of the GMT's 8.4-meter segments forms a separate image of the observed object. These images are then superimposed, increasing overall brightness and improving resolution. The secondary mirror also consists of 7 segments, each corresponding to a specific primary mirror segment. Light reflected from one of the 8.4-meter mirrors is directed towards a specific segment of the secondary mirror. These secondary mirrors, equipped with an adaptive optics system, align the light beam and concentrate it before it reaches the scientific instruments. Thus, all 7 segments work together as a single monolithic mirror, just over 25 meters in diameter. However, due to the gaps between the segments, such a mirror collects less light than a solid one. Nevertheless, this is sufficient for studying the universe in previously inaccessible detail. For optimal system performance, all 7 mirrors must have the correct shape. The telescope's optical system is a Gregorian type, which differs from Cassegrain telescopes by having concave primary and secondary mirrors. Light, after reflecting off the primary mirror, is focused in front of the secondary mirror, and then refocused within the scientific instruments. This design ensures clear images of objects across a wide field of view. The concave secondary mirror facilitates the calibration of scientific instruments and enhances the performance of adaptive optics, which compensates for atmospheric turbulence. Producing a 20-ton glass mirror of the required shape is a complex engineering feat. The only place where this is done is the Mirror Lab at the University of Arizona in the USA. Beneath the university stadium lies a giant rotating furnace used to fabricate mirrors for the world's most powerful telescopes, including the Large Binocular Telescope in Arizona, the Magellan Telescopes in Chile, and the Vera C. Rubin Observatory. High-quality mirrors are made from O'Hara E6 glass, known for its purity and resistance to thermal expansion. The glass is manufactured in Japan as large, handcrafted pots. After breaking the pots, the monolithic glass is cut into pieces weighing 4 to 5 kilograms, which are then shipped to Tucson, Arizona. There, technicians manually load the glass pieces, totaling about 20 tons, into the large furnace. For several weeks, the furnace rotates and heats up to approximately 1,100 degrees Celsius, allowing the glass blocks to melt and acquire a honey-like consistency. The furnace's rotation helps the mirror maintain the necessary shape, pushing glass from the center and raising it along the edges, forming a concave parabolic shape. This avoids the need to polish several tons of glass. The mirror then cools slowly for a month and a half and is prepared for polishing, the longest stage, which can take over a year. The ideal concave shape is suitable only for the central mirror, while the other mirrors must have a different, potato chip-like shape. Grinding such a shape requires significant time and effort. As a result of polishing, the mirror becomes 3 tons lighter, and its surface is perfected to within 20 nanometers of irregularities. The finished mirror is packed into a container and shipped to Chile, where it will be installed at the Las Campanas Observatory, located in the southern outskirts of the Atacama Desert, one of the driest places on Earth. The dry air in Atacama reduces light absorption and lowers the probability of cloud formation. Furthermore, its remoteness from major cities minimizes light pollution, and the stable climate is favorable for mirrors, which can deform due to sudden temperature changes. It is no surprise that Atacama concentrates the world's best observatories, including the European Southern Observatory's extremely large telescope, currently under construction. By 2030, Chile will host approximately 70% of the world's astronomical infrastructure. From a scientific perspective, the Southern Hemisphere offers a unique platform for astronomical observations. Its location on this part of the globe provides a view of cosmic regions hidden from observers in the Northern Hemisphere. Here, astronomers can study the galactic center, home to the supermassive black hole Sagittarius A star. Additionally, Proxima Centauri, the closest star to our Sun, and its planets, the closest exoplanets to Earth, are located in the Southern Hemisphere. Not to be forgotten are the Magellanic Clouds and other dwarf galaxies, observable only from the Southern Hemisphere. One of the key advantages for positioning astronomical observatories is the Chilean Andes, characterized by low humidity and high altitude. It is here, on a mountain 2,500 meters high, that the Giant Magellan Telescope, GMT, will be located. The telescope's altitude is crucial as it minimizes the atmosphere's impact on the quality of astronomical observations. Earth's atmosphere, despite being essential for life, creates significant interference when studying distant exoplanets. Uneven air currents distort light from astronomical objects, leading to blurred images. In the late 1980s, technology was developed to partially compensate for this effect. Adaptive optics (AO) is a system that uses thin mirrors that dynamically change their shape in response to atmospheric movement. In the GMT, this technology will be implemented on the secondary mirror, where each segment will be about a meter in diameter and only 2 millimeters thick. On the back of each segment, 675 magnets will be installed, controlled by electromagnetic actuators. These magnets will push or pull corresponding areas of the mirror, changing its shape up to 2,000 times per second to compensate for atmospheric distortions. Monitoring changes in the atmosphere requires a reference star of sufficient brightness. However, there are few such stars in the sky, covering only 5 to 10% of the celestial sphere. Therefore, modern telescopes use their own stars, created by lasers directed along the line of sight. The GMT will be equipped with 6 laser beams, covering the entire area of the sky to be observed. Thanks to the telescope's Gregorian design, the GMT's adaptive optics will be able to calibrate the incoming light more effectively than Cassegrain telescopes, as sensors can be placed directly at the primary focus before the secondary mirror. New algorithms and miniature electric actuators will allow the GMT to capture images of new quality, surpassing even the capabilities of the James Webb Space Telescope. However, it is worth noting that the James Webb can observe infrared radiation, which is inaccessible to ground-based telescopes. It is designed to observe extremely faint objects, whose light originates from the time of the first galaxy formation. No ground-based telescope can match it in this regard, as Earth's atmosphere is opaque to many wavelengths. The GMT compensates for this with high resolution, opening new possibilities, for example, in the search for exoplanets. The scientific goals of the GMT construction span all areas of astronomy, but particular attention will be paid to the study of planets and their properties. The observatory's main scientific instrument will be a large spectrograph, designed to search for Earth-like worlds and biosignatures in their atmospheres. Astronomers hope to detect oxygen molecules, which accumulate in Earth's atmosphere due to the activity of living organisms. However, oxygen is not an ideal biomarker, as it can also form from geological processes. Furthermore, life on Earth thrived for billions of years before photosynthesis saturated the atmosphere with oxygen. Therefore, anaerobic bacteria, which dominated Earth in its early epochs, could very well exist on other planets. Methane can be considered an alternative biomarker, especially if it is present in the atmosphere along with carbon dioxide. In addition to atmospheric research, the GMT will be able to obtain direct images of planets thanks to its coronagraph. Given the telescope's high resolution, we can expect to see many more direct images of planets, which are currently a rarity. The GMT will be able to accommodate up to 10 scientific instruments, operating in the visible and mid-infrared ranges. Initial observations using 4 of the 7 mirrors are expected to begin in the early 2030s. This will be sufficient to commence operations while the remaining mirrors are being manufactured. Once all mirrors are installed, astronomers will have a powerful instrument that will allow them to view the universe in unprecedented detail. And that concludes another episode. The team bids farewell to its listeners or readers, depending on the format, and expresses hope for an upcoming reunion in the next installment. We encourage you to prioritize your health and well-being. Until next time, on air or in print.